Hello, guys. Can you guys hear me?
Yes.
Yep, we can hear you.
Yes.
I think people are starting to come in, so feel free to get started at any point in time.
Yeah, so I think we have been seeing many wonderful talks from different aspects. I think one theme we see over and over again is that various projects and people working on the different level of abstractions. Some of the higher, I think Eduardo, he's working on the highest level abstractions, which is building a Lisp-like front-end language for all the DK, which is super cool. Like myself is a Lisp scheme and Racket fan. It's great to see the revival of the Lisp in the ZK age. And me, Brendan, we're working on the intermediate representation levels, which is an interesting topic because it's neither kind of user facing nor very low end. Not very like a super backend like assembly and proof system. And Bowen and Rahul are working on hardware. I guess Rahul working on various spectrum of abstractions as well, but working a lot on hardware, right? One thing we want to discuss today here is that what's the future look like, right? Because there are so many moving parts, and also there are like a lot of moving targets to choose, both from the front end language and also the IR, and also the backend the proof system primitives. I feel like this is like three moving pieces all together, and we're trying to building stuff. So that gives the I think that will brings a very interesting perspective for this discussion today. Is that for example, like what should we do, right? Given this, hey Brian, yeah, I just recap a little bit. Saying both in terms of the ZK abstractions, both in terms of front-end language to the intermediate representation, to the backend proof system, even to the hardware. These are the moving pieces together. And it's great, like all of you guys speak today. And this discussion we want to see, asking an interesting question, right? Because there's so many moving parts. What should we do? The first topic I want to raise here is if you look at from the kind of like from first principle, how do you express computation or kind of a relation in zero-knowledge proof systems, right? Where actually there are kind of three, I would say three different kind of things. First is like R1CS and quadratic constraint system. And then we have kind of like a Planck-ish arithmetization. So you have custom gate, you have lookup tables. You kind of like not exactly a state machine, but it's kind of like a mixture of arithmetic and state machine model. And then the other end of the spectrum is a Stark. Like then kind of like a people rather in terms of thinking of Stark as a constraint system is more kind of like a state machine, right? These are all the actual things we're modeling. So in that sense, right? So this seems to be a wide spectrum of the kind of computation or target we're supporting, semantic we're supporting, right? I think it would be interesting from the like. I know like Brian is a big fan of MLIR, right? But I just want to pass this topic to everyone, maybe starting from Brian. Like, what do you think the IR should look like? Do you think there is a unified IR to rule out all, or we just like, or it's fine to have different IRs, or what's? I think that's a first topic I want to raise here. Brian, do you want to share some of your thoughts?
Sure. And look, I think it's fine to have multiple IRs. I think that's kind of, in one sense, that's like the point of, the MLIR and sort of infrastructure there, especially this early in sort of the evolution of kind of technology. I guess the question in my mind about like at what point, should there like be more settlement around what IRs exist and how utile they are has a lot to do with like at what point the math kind of stops evolving. And so that's the big like X factor in my mind. Are we gonna see, like, I guess, I don't know, it seems like it's changed a lot in the last couple of years. I don't know that it's gonna radically change, but it could. So I don't know.
I guess this is like, let me ask a more specific question here. Do you think there's some hope we have some like representation can unify at least snark and stark? Or because, I mean, also feel free to chime in, guys. Like, or do you guys think, hey, this, at least for the stark and snark, we should have, I mean, it's better to have different like representations and compilation pipeline for the from the engineering and programming abstraction point of view.
I think one thing I think is not been totally explored yet is like the fact that Plonk and Stark can still share the same techniques in terms of what the underlying quotient polynomial contains in it. I think that just the idea, like the main idea that I got from Plonk is that, okay, now you can just do anything because you can put anything you want in the quotient polynomial. So you just mix and match what you want, and Stark just happens to be this set, and Plonk, vanilla Plonk is that other set. You sort of can do it anything you want. And so I think if there's like a set of specific kinds of techniques that we want to keep, so for example, the Stark, row by row transition, things like lookup tables, things like permutation arguments, like we'll sort of settle on those, maybe like 3 or 4 of those, and then the IR will be something like, okay, maybe an IR for each one of these kinds of concepts. So like an IR for custom polynomial-based gates, then IRs for like lookup tables, and IRs for row-by-row transitions, and then sort of this global IR is just like, okay, which ones am I picking for my specific use case? But maybe there's an IR for each kind of technique, something like that. I think that could be an interesting place to divide the problem up.
Yeah, I mean, I think that mirrors like how you've seen some of the evolution of like which IRs exist at which levels of abstraction in the LLVM eco and sort of AI ecosystem, at least, for sure. People settle on, is the Linalg dialect the right level of abstraction or not? Well, for some problems, yes, but maybe this like affine polynomial dialect is useful for merging loops and so forth. So I do think you start to see like IRs or dialects that are specific to the sort of underlying problem, and then figuring out how to combine them is like the role of a higher level infrastructure, which I then think useful for like helping hardware developers figure out how to build hardware, right? Because these sort of core low level like entities you're talking about are the things that you have to accelerate and then also figure out how to pass sort of data between and connect.
Yeah, I agree a lot. Also, I think there should be some like a glue code IR to stitch kind of like all these IR together, like Brian just said, for the like mirror. Or I think if people haven't worked like deeply enough in the compiler pipeline, I actually see the like LLVM or mirror style compiler construction. I didn't realize like LLVM is not a compiler; it's a compiler framework, and MIR is not a IR; it's an IR framework. You can have extensions, and it can have multiple extensions and dellet. And if people are familiar with Haskell, know this kind of like a template Haskell library, you can actually having some like a meta like definitions of the IRs to define like what's this specific IR look like, and then this brings a lot of flexibilities. I guess a question for Brian: what is the MIR you guys currently have built? Do you think what is a kind of good part and bad part you guys find using LLVM like MLIR in the engineering practice?
Yeah, I think the bad part is that it's quite a bit of developer overhead to learn what you're doing. And if there's a lot of dialogue, if there's like a lot of churn in IRs and dialects, and you have a bunch of like passes to convert between them, then that can be difficult to keep up with. When the infrastructure there was less mature, there's a lot of churn from just sort of core concepts changing, but that seems to have mostly gone away. So I would just say it's really just kind of, it's pretty intimidating from the outset, from both a tooling perspective and sort of like understanding lit and all of the table infrastructure. Yeah.
So for example, I would imagine MLIR is not really built for polynomials, and you guys probably need to build some extensions for polynomials, or it is not a problem?
Yeah, no, I mean, you can really represent anything in kind of the point. Like if you look at the stuff people have built around the kind of tensor abstractions and like Einsteinian like tensor notation for affine access patterns over like tensors, it's very, very flexible. It's yeah. So I don't think there's, you could build a specific dialect to talk about polynomials. I think there's actually some examples of people like building calculator dialects and stuff like that. So it's very general infrastructure.
Got you. Yeah. So I guess that's definitely very good to hear. So then I would like to ask Eduardo, from the front-end language point of view, like what do you think about in terms of the intermediate representation, right? What are the pain point you see? I guess you guys, LARC is majorly target to Nova, right? So
yes.
any particular reason? Yeah, sorry.
We target Nova and Graph 16. We also plan to have more backends, and it would be nice to have a good intermediate representation for that. But it's a trade-off, as always. So we have some simple representations, as for example, R1CS, but we also have more complicated representations that allows us to do specialized tasks. So it's hard to tell what's going to happen, but it's good and natural to have both things together. And I think it's even better to have more options for now. And then later, things are going to converge. And for LURC, I believe we need to support many different targets. And so it's good to see things like we saw today, like the middleware, so that it allows us to avoid wasting time doing the same thing that others did. So that's my point of view. Yeah.
Got you. So now that maybe we can switch the gear a little bit, right? So they're talking about moving target. So there are a bunch of incoming sort of innovation on the proof system side, right? And I think several particular things, at least in my list, seems very interesting. First is the hyperplunk, which is get rid of FFT or NTT in the proof system and like underlying proof systems. And second is so there are quite some discussions about lookup singularity. The idea here is that there are more like advanced lookup argument, like calc, like BLU, the research paper coming out. So these lookup arguments are quite different than the previous ones because they are optimal in a different sense. So previous lookup argument, the efficiency is with regard to the size of table. And now this lookup argument called optimal lookup argument, and these efficiencies are with regard to the size of opening. And so that's quite amazing. It's basically people get the Cauchy linear like efficiency in regard of the regard of the size of opening. And the third trend I can see is that seems that Goldilocks field get a lot of love. We have seen quite some talk today, and the proof system like Plunky 2 get amazing concrete efficiency, and Goldilocks seems to be like getting quite some adoptions, right? All these trends, right? So I guess from the I would like to ask the folks working on the hardware side, right? How do you guys see this as like will affect the hardware acceleration designs, or it's no impact at all? That's a second thing I want to throw up here.
Yeah, actually, we have finished a preliminary hyperplunk hardware acceleration solution internally, but we didn't publicly release that. So based on our engineering efforts and founding, we believe that, of course, hyperplunk is getting rid of the NTT parts of the traditional proof system from Halo 2, but it introduced a new kernel which is called MLE. And based on our founding, we found that MLE it's basically a submodule of the MSM hardware acceleration solution, which means that MLE could be absorbed into the existing MSM hardware acceleration design. And it won't be costing hardware more than a little, I would say. But the problem is that the performance bottleneck of the MLE changed quite a bit. So the performance bottleneck for the NTT design is actually on its memory access path, is on its memory bandwidth, as we all know. And the design of MLE, it's shifting the performance bottleneck from memory access to I/O bandwidth, which is PCIe connectivity between your hardware accelerator card with the traditional CPU chip. And that would be a problem for us because it's like putting the same kind of limitation on all hardware vendors, including FPGA, GPU, and ASICs. And it will be forcing GPU, FPGA, and ASICs to be like running basically at the same level of speed. And that could be an interesting characteristics from our hardware perspective. That may be welcomed by the community, maybe, or the community would say, no, it's not enough. Maybe the community wants higher performance because the community wants to have higher TPS for the entire proof system. So maybe you guys might want to lift that limitation on the PCIe bandwidth, because PCIe bandwidth is having a hard time to be improved during the last decades. We got huge problem on signal integrity and power delivery and so forth. A lot of problems going on, and you just can't bet on the mass like this. So PCIe speeds will be really hard to improve. And even if we can improve the PCIe speed, it will be costing us like easily like $5 billion into delivering just a higher PCIe bandwidth.
Right. I mean,
so
this is why
yeah.
Oh, sorry, go ahead.
Yeah. So which means if the community choose to migrate on the hyperplunk proof system, then the community should be prepared to see the same level of performance from FPGA, GPU, and ASIC, because all the ones are capped by the PCIe speed. Yeah.
Yeah, I think just to add to that, that's why you've seen things like NVLink and like Cerebras with wafer scale computing and things like this sort of evolve in the ML space, right? People start to build these like excessively, I don't say excessively complex, but extraordinarily complex interlink systems to deal with sort of I/O bandwidth between components. And I do think that's like thinking from the sort of hardware software co-design sort of stuff I was talking about earlier.
Yeah.
It's really important to have this set of use cases if you're trying to build hardware, and then have some notion of like how they boil down. And when you start to think about like proof system interoperation and certain problems maybe making sense for different proof systems. It just really depends on, whether ZK becomes kind of a niche thing for accelerating blockchains, or whether, verifiable decentralized computation becomes like a key.
Right, definitely. Yeah. That's a really good point. Yeah. So NVLink it's a really good thing to have, but the problem is that it's 20 times more expensive than traditional GPU card. So which means that will be really hard for individuals within the community to join the game of mining. I think it will be really bad for the community to see or be just several really big players who can join the game of mining. That would be really bad for the community. Yeah. So eventually, I would say, I think every one of us agree that eventually we will see a really decentralized proving network, and that means our hardware should be really cheap. Otherwise, everyone will be just paying off for NVIDIA. Yeah, that's really bad.
That's actually a very interesting perspective, right? Because the sort of the sales pitch for Hyperplunk is that hey, we're getting rid of the NTT, and the MSM is massive parallel, and it's hardware friendly. So that's why we're doing this, right? From your description, I kind of see a gap between the intended design goal of the Hyperplunk and the actual seems the practical implication of Hyperplunk, right? So
right.
I mean, we may have some improved proof system design over the existing Hyperplunk can sort of mediate the game. But what you are saying right now is that despite we have this current version of a Hyperplunk design, it doesn't seem to fully deliver its promise, which is have like a massively parallel, hardware-friendly, or like entity-free. Despite it's entity-free, it's kind of shifting the bottleneck from memory bandwidth to I/O bandwidth, which is arguably worse, right? Because you would rather be bottlenecked by memory bandwidth rather than I/O bandwidth.
Right, because so for ASIC design, memory bandwidth is a thing that you pay for more money, then you get higher memory bandwidth. That's basically a money game. And for PCIe, PCIe has a standard, and the upper bound I/O bandwidth is approximately 32 to 64 gigabytes per second, and so that's same for everyone. And that's not a thing that you can change with your money. And if you really that rich, you can just go out to buy the NVLink, as Brain just pointed out. That's a really good point. But you should be prepared to pay 20 times higher price, and that's what NVIDIA is asking for every one of us. And that would be really bad for a decentralized, eventually decentralized landscape of the proven network. And that will be hard for individuals, and maybe still acceptable for hardware company, but definitely not for individuals. Yeah.
Got you. Yeah, I feel like that's quite interesting. I think you should write a blog article and get some feedback to the proof system designers. I actually see a gap of the intended proof system design and the actual like effect of what is like the current scheme have.
Yes. So I would say the next step might be that so the community might design the next generation proof system with hardware vendors, so that eventually we can actually as a hardware vendor, we will be able to deliver a cheap, really cheap, accessible hardware for everyone in this community, and everyone will be better off. Otherwise, then we will be just repeating the tragic scenario from the last decade, is that we're just paying money for NVIDIA for those GPUs. Yeah, that would be bad. Yeah.
Right. Yeah. That's a very interesting perspective. So I guess The next is about like Goldilocks, right? So we're talking about hyperplug, right? I guess we'd love to hear from Rahul and Bowen, like, because seems like Goldilocks field pick a lot of great usage. Polygon team are pushing that moving forward, and I'm not sure this is disclosed, but I've seen a few other projects are picking up Goldilocks field, right? So that seems to be quite friendly to hardware. So like, would love to see you guys' perspective on this kind of like the adaptation, the adoption of the Goldilocks field in this field, and how does that impact the hardware accelerator and in general the prover market side?
Yeah, I agree at a couple points as well on the hyperplug side. I think it's actually pretty interesting to see like the comparisons between the FPGA and GPU side, because there's such limited PCIe bandwidth. At least on the FPGA side, like PCIe on FPGAs hasn't like really developed in the last few years, and so you're stuck with things like 2.5 gigabytes per second on some of the older boards, and I think like even in the ones that are provided in cloud services are pretty limited as well. So I think you're stuck with like PCIe 3 on there, and so like at least for things like hyperplug, which aim to sort of parallelize the MSM, the computation by just using MSM. I think like if you're able to turn something in a memory bound algorithm into more of an IO bound algorithm, I think it's probably more efficient to do this on GPU, and I think that's probably going to be the more like near term use case, especially because some of the newer GPUs have the 32 to 64 gigabytes per second on PCIe. But fundamentally, like I don't know if that's the question I have is, can we even get around this issue practically, like as an industry, like can we get over this like IO bandwidth issue, which I'm not sure is possible without some of the larger players finding a reason to actually develop in this market. And it's because like we have to prove over these like large instances, right? So I mean, if you can sort of split up your computation as well into smaller instances, and you can combine them later, then you can also make a case for saying, okay, I don't need as much IO bandwidth as possible. But I think we're just under that threshold right now. I'm curious to hear other people's thoughts on this.
Sorry, I think most people agree with what you said. That's a very based.
All right.
Yeah, just use recursion for everything. Solves the IO bandwidth problem.
Yeah, exactly.
There you go.
Yeah.
All right. Yeah. Like.
Yeah. Oh yeah. Yeah. Let me just follow up on the Goldilocks point. I think obviously like I personally got excited about the Goldilocks field from just seeing some of the stuff with NTT. I mean, I'll just say like in hardware, for example, like when you're trying to when we were talking about the Cyclone NTT design, like what was sort of relevant when we were trying to build this thing. And I think there's like one component was the fact that obviously you can do these modular reductions like quite efficiently. The prime is just very amenable to it, so you can just subtract 2 to 32 minus 1, and suddenly you've done your modular reduction, and everything is like nice. The other component is that because the field size is so small, like you have these ports on your FPGA, you have memory, and like usually the memory interface is like 512 bits, and this happens to be 64 bits, so we can fit multiple FIFOs in the same like sort of memory interface, as opposed to having just one FIFO there. And so you have a lot of this like these optimizations that you can just use because it just is a smaller field size, and so that happens to be something that's very useful. And I think smaller field sizes in general probably will be extremely useful for hardware applications, but obviously there's trade-offs on the security side as well.
Right, like we chose our field size, which we called Baby Bear, kind of late, I guess, because it's very small relative to Goldilocks. Right, that was designed, like we chose that one specifically because it would be more amenable to optimization on the current class of consumer grade GPUs, which intentionally kind of have their N64 units disabled or under like 8x underclocked. So that said, Goldilocks is also really promising. So it's it's an interesting question long term as to what kind of fields make sense in which applications, especially when you can use recursion to like mush everything together.
Yeah. I think thanks a lot for the discussion here. We are getting to the end. Before everyone go, I just want to see, because we're covering a lot of stuff here, I just want maybe from Brandon, and to see, just use one sentence to describe what do you think for people are in this either like high level language, IR, and the hardware. What do you think is going to happen in the next, let's say 3 years? I think 5 years is too far. This field is moving too fast.
Yeah, I mean, what I expect to see or what I hope to see, I mean, they're necessarily the same thing, but
maybe
I think,
both.
yeah, I think composition and like all the stuff with recursion is going to be a big deal, and especially, you know, one thing, we're part of the Xerox Park Squad, and this is like the whole theme of their next like 6 months is like, can we improve proof composition recursion? And I think this will also solve a lot of the even the IR questions as well, because basically what's going to happen is people are going to be building recursive verifiers for all these different systems, and what you'll have to do is you'll have to encode the proof system in a circuit, and circuits are sort of very constrained in their representation, and so you have to come up with a representation that sort of like fits all these constraints. And I think one thing you could maybe do is see how people are building the recursive verifiers and actually extract an IR from that, because they're already sort of doing that in the act of, you know, like building the recursive verifier. So and one thing I really hope we can do is sort of get this merge of like Planck and Stark into like one unified concept. I think this just like, it's sort of like a categorical error to think of them as separate things. And I really like, if we can do that, then I think the IR will sort of fall out, you know, it'll just fall out. But we still have this, still obviously 2 domains here, like R1CS is clearly something completely different. But yeah, for the Planck side, I think there's a lot of hope, I think, for me at least, in the next 3 years, that we can get an IR that makes a lot of sense. Yeah.
Perfect. That's way more than one sentence. But,
oh, sorry. Yeah.
But proof aggregation and unify using
proof aggregation, unify
using,
Planck and Stark. Yeah.
Okay. Perfect. Rahul.
No, I think probably, yeah, I would say proof aggregation is definitely, and I think convergence on like sort of infrastructure and tooling, I think will be important.
Great. Seems we have an agreement here. It's less dramatic than I expected, but that's great. Sorry, how should I pronounce your name?
Eduardo.
Eduardo?
Yeah. That's
what's your take?
I think we need to keep an eye on the ZKP standardization effort. Mm-hmm. They are going to analyze things in detail, so it's good to see what they are writing in the standard. And I think we are going to see a lot of hardware acceleration and integration of different projects to avoid wasting effort. But I think the way to do that is to pay attention to the ZKP standardization effort.
Great. That's a standardization and avoid waste effort. Brian?
Yeah, I think I agree with pretty much everything everybody else said, but the thing that I'm going to be keeping my eye on really is like how, especially with the demise of SGX, you know, how important ZK computing becomes, not just inside the Web3 community, but outside the Web3 community, and how much of a disruptive technology it really is. You know, I think Gartner has its own idea of where it is on the hype cycle. The question is like, are they right? And it's kind of like, oh, well, that was kind of interesting, or is there really going to be a sort of explosion of use cases for ZK? And I think that's going to really drive a huge amount of the sort of discussion around all the things we've been discussing today.
Great. Yeah, that's definitely a fresh take. Non Web3 application with ZK. I'm also pretty excited about that
I
too.
mean, and also the expansion of applications inside Web3 and the blurring of those lines, I think.
Mhm. Perfect. I guess last but not least, Bowen.
Yeah. So I agree with most of the points about, and I just want to add a one of the I would say, let's say, personal hope is that during the next 3 to 5 years, as a community, we can attract like 1 billion users into our community, and in that case, we will see a huge boost in the entire demand across the board, from software to hardware. And only in that case, I would say we will really see a boom in for this entire ZKP community, and especially for hardware, because hardware can only survive in such a huge market. Yeah.
Yeah, that's also very base take. All right, thanks so much for everyone. It's a very, very fun discussion. I learned a lot from you guys, and let's end up here. And I will ask Kenny to take over.
Thanks for putting all this together,
Thanks.
Shumo.
Thank you, guys.
Yeah, thanks, guys.
Bye.
Bye.
Thanks.
All right. Thank you, guys. Feel free to stay on, or, I know it's been a lot of your time already. Really appreciate all the time that you've put into this conference. Thank you for attending. Thank you for sharing all the innovation and the stuff that you're working on. And I think that this was an amazing wrap up for the first OpenZL conference, one of many. Saw that person running around behind you, Eduardo. Good attempt.
Yeah.
That's a very nice physical representation of ZK in action. But with that being said, I think that we'll conclude here. We have one final challenge, which we will open up to the entire community. And that final challenge is specifically just, tweet about some of the key points that you learned from the conference today, and tag OpenZL, and we'll be selecting someone from there as the winner. And with that being said, thank you so much for everyone attending this conference. I know you're from all different time zones, all different walks of the world. So really appreciate your time here and staying up and getting some knowledge on the ZK side. And we hope to see you again shortly in the next OpenZL conference. Thank you, guys, and have a nice day.